Hello everyone, greetings. I'm Deepa from the PG and Research Department of Biotechnology. The topic I'm going to take is about hydrogels. Hydrogels are three-dimensional structured networks. They are made up of cross-linked hydrophilic polymer matrices. These hydrogels are capable of holding a large amount of water, that is up to 99%. These hydrogels displays useful characteristics like softness, toughness, biocompatibility, stretchability, and deformability. The cross-linking among the hydrophilic functionalities facilitates their structural integrity and prevents their immediate dissolution in the aqueous environment. That is, cross-linking plays a vital role in withholding their structures. These hydrogels they have the ability to entrap and preserve a substantial amount of water or biological solutions. This unique combination of softness and flexibility are similar to natural soft tissues and thus make them promising materials to mimic their properties. To say it simply, we can say hydrogel is a biocompatible hydrophilic polymer that resembles soft tissues. Apart from these characteristics or properties, the hydrogel shows exceptional other properties also like physicochemical properties, mechanical properties, optical properties, and biocompatibility. Coming to the physicochemical properties, it includes swelling and permeability, mechanical properties, example like stretchability, optical properties, they show the interaction with light and biocompatibility. Biocompatible means it is the ability to be in contact with living system. So coming to the hydrogels, they have made them a flexible tool for applications such as imaging, diagnosis and treatment. Hydrogels can be fabricated into thin films or molded into any shape, size, length, or different architectures depending on the environment or requirement. To say it simply, hydrogel can be made into any shape or size that you desire. The high absorption water absorption of hydrogels are due to the presence of their hydrophilic functionalities. These hydrophilic functionalities are because of the groups like hydroxyl, carboxyl, amide, amino, sulfur, etc. These hydrogel networks are designed with diverse polymers of natural or synthetic origin to form a hybrid structure, which is utilized to support, protect, or attach new functionalities to the hydrogel structure. Okay, so these hydrogel networks they can be formed from varieties of polymers and they may be natural or synthetic or hybrid. Okay, most of the polymers that are used for the hydrogel preparation are non-toxic and are considered suitable for many biomedical applications like skin patches to implants. This slide shows the picture of hydrogels. The next one is the recent advancements in medical field have utilized numerous hydrogel based products for the treatment of patients. For example, polysaccharide like chitosan, alginate, cellulose, etc. based hydrogel have been extensively used for wound dressing and poly 2-hydroxymethyl methacrylate hydrogel is typically used for contact lenses. Hyaluronic acid hydrogels for drug delivery systems. Proteins like gelatin, collagen, and fibrin based hydrogels or scaffolds have been used for tissue engineering. For the treatment of cancers or tumors, the drugs to be treated are incorporated within a hydrogel and they are injected directly to the tumor site or adjacent sites, restricting the toxicity of the drugs to the localized area where tumor cells persist. So, these hydrogels are very widely used in drug delivery. This slide shows about the history of these hydrogels. The term hydrogel can be tracked back to 1894 and was first used to describe a colloid of some inorganic salts. The first ever hydrogel reported in 1949 for biomedical implant was Evolon. It is made up of polyvinyl alcohol cross-linked with formaldehyde. In 1960, polyhydroxyethyl methacrylate was introduced which bring the market of hydrogel to bloom. Looking back at the history of hydrogel, these hydrogels can be roughly divided into three generations, that is first generation, second generation and third generation. So this first generation it consists of three main categories. First category includes polyacrylamide and polyhydroxyethyl methacrylate. Second category includes polyvinyl alcohol, polyethylene glycol, and these are mainly used in tissue engineering. Third category it involves cellulose based hydrogels. So these cellulose based hydrogels are mainly used as drug dispersion matrices in drug delivery. The next is the second generation. So the second generation includes PEG and polyester block copolymers, which convert the chemical energy of the hydrogen into the mechanical energy of the hydrogen to achieve the specified function. These types of hydrogels can be listed as stimuli responsive hydrogels and they are available in market since 1970s. Stimuli responsive hydrogels can be classified into three categories, that is temperature sensitive hydrogels, pH sensitive hydrogels, biomolecule sensitive hydrogels. And the next one is the third generation. The main application of this third generation is the preparation of injectable hydrogels by blocking two amphiphilic copolymers such as polylactic acid and poly D lactic acid. The next one we are going to see about the classification of hydrogels. The hydrogels they are mainly formed from biopolymers and polyelectrolytes. These hydrogels are categorized into many different groups depending on their origin, structure, preparation method, cross-linking, charge, responsive nature, physical aspect, and degradation. So this slide shows the different types of classification. So first one is based on source or origin. So, based on the source, the hydrogens may be classified into natural, synthetic, and semi synthetic. The next one is based on composition. It may be homopolymer, copolymer, semi IPN, and IPN. Coming to the configuration, it may be amorphous, crystalline, and semi crystalline. So, coming to the amorphous, it means it does not have any shape, form, or structure. The next one is cross linking. It may be either physical or chemical. Ionic charge, anionic, cationic, or non ionic. Response based, it may be physical, chemical, or biochemical. Degradability, it may be biodegradable or non biodegradable. Physical property, it may be conventional or smart. Now, coming to the first classification based on origin, these hydrogels may be natural or synthetic. Coming to the natural hydropolymers, they are prepared from polysaccharides like alginate, chitosan, agarose, hyaluronic acid, cellulose, etc. Proteins derived from biological sources like collagen, gelatin, elastin, fibrin, etc. Proteins like collagen and elastin are natural constituents of the extracellular matrix and often derived from animal tendons or skin or human sources, while polysaccharides for hydrogel preparation are derived from the shells of sea crustaceans, marine algae, and plants. So these natural hydrogels are biodegradable materials with good biocompatibility and low toxicity. Advantages. The main advantage of these natural hydropolymers is they naturally support cell adhesion and proliferation. Other hydrogels produced from plant based materials are readily available and avoid any kind of viral infections that may have animal origins. Limitations. So, even though they have many advantages, there are some limitations. Now, we are going to see about the limitations of the hydrogels. The undefined structure of these materials allow limited control on the mechanical properties like rigidity and flexibility. The difficulty in reproducibility in large scale production has narrowed their use in many biomedical applications. Coming to synthetic hydrogels, these are pre-structured hydrogels. Okay, so they have defined chemistry based on the structure of monomers or polymers from which they are made of. The commonly used polymers include polyethylene glycol, polyvinyl alcohol, polymethacrylic acid, poly N isopropyl lacrylamide, polyethylene oxide, polyacrylamide. Advantages. So compared to the natural hydrogels, synthetic hydrogels they possess the potential for advanced characteristic features like high water absorption capacity, improved physical and chemical stability, reproducibility, enhanced gel strength, which are enabled by their chemically cross-linked structure. The last one is the features are critical for designing tissue engineering scaffolds, drug release systems, bone implants, and biosensors. Now, coming to the limitations, so even though they have many advantages, these synthetic hydrogels possess different structural chemistries which are not always friendly to the internal cells and tissues, and they may lead to poor biological activity and compatibility. That is, they are less biocompatible compared to the natural hydrogels. In order to overcome these limitations, the current research they focus on developing biohybrids by combining natural and synthetic polymers. Hydrogel classification based on preparation method. So based on preparation method it is classified into four types. They are homopolymeric, copolymeric, and IPN hydrogels, semi-IPN. Coming to the homo means single. This type of hydrogels they are formed from single polymer with the same repeating monomers. The next one is copolymer. Co it means multi-monomeric polymers. So these copolymeric hydrogels they are made up of multi-monomeric polymers with minimum one hydrophilic polymer arranged in block random or alternating configurations. The next one is IPN. IPN means interpenetrating polymer network hydrogels. They are made from two independently cross-linked natural or synthetic polymers confined in the network structure. The next one is semi IPN. If the component is linked and the other is not linked, it is called semi IPN. The next one is the classification based on cross linking. There are many ways to cross link hydrophilic polymer chains to form stable polymer networks of hydrogels. The cross linking regulates water absorption and helps to uphold the 3D structure of hydrogels in swollen states. Among various cross-linking procedures, physical and chemical cross-linking are the most commonly used method to fabricate these hydrogels. Coming to the physical cross-linking, these physically cross-linked hydrogels they can be fabricated under very mild conditions without the need of cross-linking agents. So these cross-linking agents sometimes they may cause toxicity to cells or tissues. There are many techniques for producing physically cross-linked hydrogens. They are hydrogen bonding, ionic electrostatic interactions, freezing thawing, hydrophobic interactions, charge interactions, stereocomplexing, protein interaction, and crystallization. The next one is chemical cross-linking. Chemically cross-linked hydrogel they consist of covalently cross-linked network. Okay, so the main thing is this chemically cross-linked hydrogels they are made up of covalently cross-linked network, and the bonds are much stronger and often more stable than those of physically cross-linked hydrogels. So compared to the physical cross-linked hydrogels, chemical cross-linked hydrogels are very stable and are very strong. The chemical cross-links are produced in a number of ways like copolymerization of multifunctional monomers, reactions with cross-linkers, application of high energy radiation, chemical reactions of pendant groups. The next one is classification based on charge. Hydrogels may be classified into anionic, cationic, neutral, and ampholytic. So you all know what is anionic, cationic, okay? Neutral. Ampholytic means capable of ionizing both anions and cations. The next one, classification based on degradability. So based on degradable, it is divided into biodegradable and non-biodegradable. So coming to the biodegradable hydrogels, these hydrogels, they are formed from or synthesized from natural polymers like chitin, alginate, agarose, fibrin, and are completely biodegradable. So they will be degraded easily. Degradable gels made from soluble polymers such as PVA, PEG, PAM, and polyvinyl pyrrolidone degrade by breaking of virtual or covalent crossings. Non biodegradable hydrogels. So these hydrogels, they are made up of synthetic polymers and they are not considered environmentally friendly, but these hydrogels have been widely explored for developing drug release system, dental issues, and wound healing. The next one is the characterization of hydrogels. So, characterization means it refers to the process of analyzing and understanding their physical, chemical, mechanical, and structural properties. Okay. Then recent advancement in material chemistry and biomedical science have resulted in the development of multitude of techniques or to characterize hydrogels. So important characteristics are chemical structure, swelling, behavior, morphology, rheology, textural, thermal, and mechanical properties, biochemical biocompatibility and biodegradability. So each of these parameters they play a vital role or crucial role in building the internal design and function of the hydrogel. Some of the essential characterization methods are discussed below. So in this picture we can see how the hydrogels are characterized. So they are characterized based on the swelling, texture, morphology, mechanical properties, structure, thermal analysis and biocompatibility. Finally, we are going to see about applications in the biomedical field. So these hydrogels are included in delivering drugs or cells, drug delivery, cardiac repair, bone tissue repair, osteoarthritis cartilage damage repair, hydrogel mediated delivery of interventions, biomonitoring, regenerating hard and soft tissues, adhering to wet tissues, preventing bleeding, that is hemostasis, providing contrast during imaging, protecting tissues or organs, improving the biocompatibility, medical dressing, pulp regeneration, neural tissue repair, and spinal cord injury. Thank you.